Welcome to section 0.5, one-to-one functions, inverses, and logarithms. After today, students will be able to identify one-to-one functions, calculate inverse functions, and solve logarithmic functions. One-to-one functions. A function is one-to-one if each y value is paired with exactly one x value. What is an example of a function that is not one-to-one? And for me, one of those that's definitely not one-to-one is a parabola. Parabolas are not one-to-one because you're going to be going to the same y values on both sides of the vertex. How can you tell if a function is one-to-one? Just by looking at its graph. If, when you're looking at the graph, it changes direction on the y-axis, like it's going down and then starts going back up, it will not be one-to-one because you're going to have two of the same y values. So if you ever see the change in direction on the y-axis where it's going down and then going up, or going up and then starts going down, it will not be one-to-one. You'll also see if any graphs that you look at have a flat spot in them where they go horizontally for any period of time, then that again will not be one-to-one because you will have the same y value more than once. So looking at these two graphs, like I said, the parabola on the left is not one-to-one because you have the same y values, and the one on the right is one-to-one. One of those things you can do for a one-to-one graph is use what we call the horizontal line test. If it passes the horizontal line test, where a horizontal line only touches the graph once, it is one-to-one. Next, we are going to look at finding inverses. And there are 3 steps to finding the inverse of a function. First, we're going to switch the x and y variables. Then we're going to solve for y. And then to check it, we will compose the answer with the original function to see if we get the identity function back out, which is x. To convert it, we'll do steps 1 and 2. To check it, we will do step 3. So let's find the inverse of f and check it using function composition. So step number 1 says to change the variables. Remember, this f of x is the same as y equals. So we are now going to rewrite this with x equal to y plus 3 over y minus 2. We need to solve for y. So we're going to multiply both sides by y minus 2. We have x, y minus 2 equals y plus 3. We will distribute our x. We have xy minus 2x equals y plus 3. We will now get the y's on one side and everything else on the other. So we're going to subtract y from both sides and add 2x to both sides. When we do this, we're going to subtract the y from both sides. We get xy minus y equals, we're going to add 2x to both sides to move it, 2x plus 3. We will then factor out a y on the left side, giving us y. X minus 1 equals 2x plus 3. And then we'll divide both sides by x minus 1, giving us y equals 2x plus 3 over x minus 1. We will relabel this. This is our inverse function. We're going to say f inverse x, if it lets me write, is equal to 2x plus 3 over x minus 1. There is my inverse function. Now it says to check it by using function composition. So we're going to take the f of f inverse of x, and we're going to see what we get. So what we're going to do is we're going to take our original function and plug in 2x plus 3, x minus 1 for each of our x's. So we're going to plug them into here. So our first x becomes 2x plus 3 over x minus 1 plus 3 all over, we're going to replace that x again with 2x plus 3 over x minus 1 minus 2. So this is my composite function. Now we're going to go through and try to simplify this. To get rid of these x minus 1s, I'm going to multiply both top and bottom by x minus 1. When I multiply the 2x plus 3 over x minus 1 by x minus 1, put this in parentheses, we get back 2x plus 3. The x minus 1s cancel out. When I multiply x minus 1 times 3, I get 3x minus 3. Now I'll do the same thing to the denominator. X minus 1 times our first term, 2x plus 3 over x minus 1. X minus 1s cancel. I get 2x plus 3. Take negative 2 times x minus 1, we get negative 2x. And we have negative 2 times negative 1 is positive 2. Now we're going to combine our like terms. We have 2x and 3x. We get 5x. 3 minus 3 is 0. We have 2x minus 2x goes to 0. 3 plus 2 is 5. And we get x. And x is our identity function. So when we did the composite function f and f inverse x, we get back our identity function. And so we have proper inverses. We would check this again, doing it with f inverse x, composite with f of x. So we would do this again with f inverse of f of x to make sure it works both ways. And this one does. This is how you find the inverse function and how you check it using function composition. The next thing we will do is learn how to solve exponentials, those equations with e's in them. So e to the x plus e to the negative x equals 7. I am first going to rewrite this as e to the x plus 1 over e to the x equals 7. And then I don't like having that e to the x in the denominator, so one of those things I can do is multiply everything by e to the x to remove it. So I have e to the x, quantity squared. We then have e to the x over e to the x. And we have 7e to the x. They're going to simplify this and get everything on the left side. So we still have e to the x, and I'm going to leave it like this for now, and you'll see why in a second. E to the x over e to the x is 1. I'm going to move that 7e to the x over, so I have minus 7e to the x plus 1, all equals 0. Now what we can do with this is this thing called substitution. To make our lives easier, instead of having to work with these e to the x's, I could make this, using substitution, something that we understand how to solve. So I'm going to say that y equals e to the x. I'm going to say let y equal e to the x. Replace all my e to the x's with y's, and we get y squared minus 7y plus 1 equals 0. We now have a quadratic equation. The only thing that's different with this, it doesn't matter what variable we use here for the y's. I did not use x again. That's already been used once. But we can treat these y's sort of like we would if we had x squared minus 7x plus 1. We are now going to use the quadratic formula to solve for y. So we have y equals 7 plus or minus the square root of negative 7 squared minus 4 times a times c. So 4 times 1 times 1. All over 2 times 1. When we simplify this down, we get y equals 7 plus or minus the square root of 45 over 2. This simplifies further into 7 plus or minus 3 square root 5 over 2. So we have this. Well, now I can go back and replace my y with my e to the x. I have e to the x equals 7 plus or minus 3 square root of 5 over 2. And to solve these exponentials, to get rid of the e to the x, we take the natural log of both sides. When you take the natural log of e to the x, the ln and the e, they're inverse functions, we just get the x back. This is going to equal to ln 7 plus or minus 3 square root of 5 over 2. We're going to plug this in our calculator. Make sure you plug it in twice. One you're going to plug in is ln of 7 plus. And make sure you use parentheses. Another one will be ln of 7 minus 3 square root of 5 over 2. When you do this, you should get two answers. The first one being positive is 2.607. And the other being negative 1.925. So there we have it. Those are our solutions for solving this exponential function. The next thing we will be doing is solving a logarithmic function. And this one we're going to solve for y again. We have the ln of y plus 2 in parentheses minus the ln of 4 equals x plus the ln of x. To make this easier to work with, I'm going to move over the ln 4 to the other side. So we have ln y plus 2 equals x plus ln of x plus ln of 4. Now we have this, we're going to exponentiate both sides. So we're going to take, what that means is we're going to take e and raise it to the ln y plus 2 power equals e to the x plus ln of x plus ln of 4. On the left side, e to the ln y plus 2, the e and the ln are inverses again, so that's going to make this simplify down to y plus 2. On the right, I'm going to break these exponents down into their individual parts. So we have e to the x times e to the ln x times e to the ln 4. Remember, when you have addition in exponents, that's the same as when you have multiplication, as I've shown here. So then we have y plus 2, e to the x stays e to the x, e to the ln of x just becomes x, so times x, e to the ln 4 becomes 4, so it's times 4. So we have y plus 2 equals, I'm going to rewrite this as 4x e to the x. And then to get y by itself, we subtract 2 from both sides. We get y equals 4x e to the x minus 2. And now we have solved that logarithmic function for y. So y equals 4x e to the x minus 2. The last thing we're going to talk about is the change of base formula. On the TI-84s, there is not a very good way to enter a log with a base other than e or with the base 10. So if I want to graph the function below, I have to use the change of base formula to rewrite it so that we have it in something we can put y equals. If you try to do this on your calculator, it's not easy to put log base 3x into it. So the change of base formula is actually rather simple. We have log a to the x is the same as having ln of x over ln of a. So if I want to change this, this becomes ln of x over ln 3. And we can put that into our calculators really simply. So today we have talked about one-to-one functions. inverses and how to check them using composition of functions. And we looked at exponential and logarithmic functions and how we can rewrite them. And do some of our algebra skills we've learned in the past to simplify them, to write them in terms of other variables. That is it for section 0.5. Thank you for watching and have a nice day.